Hello there and welcome back to the Science Sleepy Minds. Tonight the stars are unusually quiet, hanging above you like scattered grains of salt on black velvet. But behind that peaceful facade, the cosmos is far from empty. Hidden behind points of light and pools of darkness are worlds, thousands of them circling stars with names like Kepler 186, Gliese 581 and TRAPPIST-1. You're not just looking at starlight anymore. You're looking at the reflected hope of humanity's biggest question: are we alone? Or even more thrilling, are we home? You probably won't survive this, not because it's scary, but because we're going to swing through solar systems where the air is poison, the gravity crushes bones, and the rain cuts like shrapnel. Sweet dreams. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know in the comments where you're watching from, and what time it is in your corner of the galaxy. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You stare up at a night sky and see nothing much, really. The stars twinkle with indifference, but your brain, wired for wonder, starts overlaying the invisible, vast planets you'll never see, orbiting suns light years away, Earth-sized rocks hurtling around red dwarfs, boiling gas giants so large they almost became stars themselves. A strange comfort washes over you, the idea that Earth is not unique, not even special possibly, just one of many, a cosmic rental property. The idea of other worlds isn't new. Ancient Greeks like Epicurus believed the universe teemed with worlds without number, some dead, some alive. Of course, historians still argue whether Epicurus really envisioned exoplanets, or just alternate Earths stacked on metaphorical shelves. Still, it's cute to imagine a toga-clad philosopher casually pondering the multiverse while chewing olives. But it wasn't until 1992, yes, 1992, the same year that Home Alone 2 hit theatres, that humanity officially found its first exoplanet. The kicker? It wasn't even orbiting a regular star. It was circling a pulsar, a dead, rapidly spinning neutron star that screams radio signals into space like some interstellar metal band. That find opened the floodgates. Astronomers suddenly realized planets weren't the rare gems they thought they were. They were more like pocket lint in the cosmic couch cushions. Now we know of over 5,500 confirmed exoplanets, and counting. Some with icy surfaces, some with scorching clouds. One even has an atmosphere laced with titanium oxide, the same stuff used in sunscreen. Yup, space is weird like that. You hover now in a thought experiment. Imagine every single star in the sky hosting at least one planet. That's already hundreds of billions of worlds in our galaxy alone. Most of them are invisible, of course. Too far, too dim, too quiet. Ghost worlds hiding behind the light. You picture them like spirits, one orbiting a blood-red dwarf, eternally bathed in rust-coloured twilight. Another locked in a tidal hug, with one side forever burning while the other freezes in shadow. Some of these planets probably have names that sound like Wi-Fi passwords. Kepler 22b, TOI 700d, LHS 1140b. Not exactly romantic, but the science behind them? Pure poetry. Then you float to a weirder thought. Maybe these planets aren't hiding. Maybe it's just us who are ill-equipped to notice them. Like trying to find fireflies using a flashlight that only sees in black and white. We're getting better though. We're starting to spot the flickers. Here's how the game works. A planet passes in front of its star, dimming the light ever so slightly. That's called a transit. You'd never notice it with your eyes, but telescopes like Kepler and TESCS, they live for that kind of whisper. Another trick is the wobble method. When a planet orbits its star, it tugs slightly, making the star dance like a tipsy uncle at a wedding. That dance gives off a telltale signal in the star's light. With enough math, and astronomers love math, you can deduce a planet's mass, orbit, and even hints about its atmosphere. But we're still mostly in the realm of inference. We haven't taken a true photograph of another Earth yet. What we have are light curves, data squiggles, and hopeful press releases. But you don't need a snapshot to believe in something. You believe in air, you believe in Wi-Fi, you can believe in exoplanets too. One strange little tidbit to file away. Ancient Mesopotamian astronomers may have noticed strange, wandering stars that behaved oddly over time. Some fringe theorists suggest they might have recorded the earliest signs of planetary transit behaviour, Do we buy that? Historians still argue whether those cuneiform tablets were math logs or just logs, literally logs. But modern scientists, they're convinced we're just scratching the surface. According to current models, there might be as many as 40 billion Earth-like planets in the Milky Way alone. Let that sink in. That's 5 Earths for every living human. You get one, Oprah gets 7. Still, Earth-like doesn't mean Earth, and that's where the real search begins. You drift now, gently, from the known into the unknown, from the comforting math of orbits to the wilder territory of what it all means. What makes a world habitable? Is it water, temperature, atmosphere, or something else entirely, some alien metric we haven't even considered yet? You brush against the idea that maybe our definition of life is too narrow. What if, on some exoplanet right now, the dominant form of intelligence is a methane-based fungus that communicates through vibration and believes stars are gods? Would we even recognize it as life, or just catalogue it as biological noise and move on? It gets lonelier the deeper you think. All those stars, all those planets, and still, silence. But also, possibility. So you stay there a little longer, suspended in starlight, letting your mind wander across ghost worlds, unseen, unvisited, and maybe, just maybe, not so lifeless after all. You hover beside a pale, distant star, drifting lazily as it pulses with gentle light. But something odd happens. Its brightness dips. Not much. Not enough to alarm anyone. Just a brief, almost imperceptible blink. And then, slowly, it returns to normal. That flicker, that was a planet. You didn't see the planet, of course. You saw what it did to the light. Welcome to the bizarre art of finding the invisible. Detecting exoplanets is a bit like solving a mystery, where the main suspect is wearing an invisibility cloak, the witnesses are drunk, and the only clue is a slight creak in the floorboards. It's subtle, it's messy, and it's astonishingly clever. You start with the most iconic method, the transit method. This is the cosmic equivalent of watching a mosquito crawl across a light bulb from 10 blocks away. When a planet crosses, or transits, in front of its star from our point of view, it blocks a fraction of the starlight. Astronomers track these tiny dips in brightness using sensitive photometers. They do this over and over, hoping for a repeating pattern that screams, "Hey, I'm a planet, I swear!" The first time this worked was back in 1999, when the Hubble Space Telescope confirmed a planet orbiting 51 Pegasi. It wasn't the first exoplanet we'd found, but it was the first time we saw one's presence through this precise flickering dance. But not all stars are cooperative. Some stars burp, others wobble, a few are just plain jerks, flickering for reasons that have nothing to do with planets. Stellar activity, like sunspots and flares, can mess with our readings. This is why astronomers are a cautious bunch. They don't announce Earth 2.0 discovered until they've triple-checked that the dip wasn't just the star having a moody Tuesday. That's where the radial velocity method steps in. Instead of watching light dim, you now listen to light change. As a planet orbits its star, its gravity tugs on the star ever so slightly. That wobble makes the star's light shift toward the blue end of the spectrum as it moves toward us, and toward the red as it moves away. A phenomenon known as the Doppler effect. Yes, the same thing that makes a passing ambulance sound weird. With enough data, you can estimate the planet's mass and orbit. Combine that with transit data, you get size, density, and even a sense of its composition. Is it rocky like Earth? Puffy like Jupiter? Made of cotton candy and broken dreams? Possibly. You're now floating inside a data stream. Endless rows of numbers, light curves, spectral shifts. It's dry stuff on paper, but in your mind's eye, it's rich. Planets forming from cosmic dust, coalescing into shapes and systems that we may never visit but can still know. That's the power of inference, and math, and a little bit of obsession. Here's a cool quirk for you. In 2007, astronomers noticed that a specific star's light was dimming in an erratic, non-periodic pattern. This wasn't your average transit. It was weird. Almost like something massive and structured was moving in front of it. Cue the speculation. Alien megastructure? Dyson sphere under construction? A galactic Home Depot? Nah, probably just a swarm of comets. Probably. Historians still argue whether this was the closest we've come to a real alien artifact sighting, or just an overexcited press cycle on a slow science week. Still, the methods are evolving. Now we have gravitational microlensing, a technique that uses Einstein's theory of relativity. Here's how it works. When a star passes in front of another, its gravity bends the background star's light like a magnifying glass. If that foreground star has a planet, it'll leave a tiny telltale blip in the lensing. It's ridiculously rare, and the alignment has to be perfect, but when it works, it lets us find planets thousands of light years away, which is both impressive and deeply frustrating because it's not like we can go visit them anytime soon. Another method uses direct imaging, which sounds deceptively easy. Just take a picture, right? Except stars are blinding and planets are dim. It's like trying to photograph a moth flying around a stadium spotlight from another continent. But with coronagraphs, devices that block the star's light, and adaptive optics, we've managed to directly image a few exoplanets. They look like fuzzy blobs, but hey, fuzzy blobs are better than imaginary ones. You pause to appreciate the absurdity. We're finding entire worlds using math, mirrors, and the fact that light is annoyingly consistent, and not just one or two, we're detecting them by the thousands. NASA's Kepler mission alone confirmed over 2,600 exoplanets during its run. That telescope just stared at a patch of sky in the constellation Cygnus for 9 years. That's it. It didn't move. It blinked at stars and waited for shadows. 9 years of cosmic voyeurism. Now we've got the Transiting Exoplanet Survey Satellite, or TESS. It's like Kepler's younger, more restless cousin. TESS scans almost the entire sky, sector by sector, looking for promising winks of light. It's already found hundreds of planet candidates, and we're just getting started. But detection is only step one. Interpretation is the real trick. Astronomers must untangle whether a dimming is caused by a planet, a binary star, dust clouds, or even instrumental noise. You wouldn't believe how often something exciting turns out to be a smudge on the detector. That's the equivalent of mistaking your fingerprint for a UFO. And then there's the ever-present limitation. We only find what we're looking for. The transit method, for example, only works when a planet's orbit is perfectly aligned with our line of sight. For every planet we find, there are dozens more we miss because their orbits are just a few degrees off. It's like watching a cosmic game of hide and seek through a pinhole. But that's the beautiful part. Every new method, every new instrument widens the peephole just a bit, and each time we find more. So now you settle into this dance of light and gravity and math, and it all starts to feel like a gentle rhythm, a lullaby of invisible worlds revealing themselves, one blink at a time. The sky above you isn't empty, it's full, you just have to know how to look. You float now near a faint twitchy star in the constellation of Virgo. It's giving off an oddly regular pulse, like a lighthouse beacon on a foggy coastline of space, and around it, something strange, a planet, but not one you'd ever visit. It's scorched, baked to hundreds of degrees, and it orbits its star in just a few days. This isn't a gentle Earth-like rock circling a friendly sun. This is 51 Pegasi b, and when astronomers first confirmed its existence back in 1995, it shocked the world. Up until that point, people assumed other planetary systems would look like ours. Small rocky planets near the star, big gassy planets farther out, and everything playing nicely on roughly circular orbits. But 51 Pegasi b, it broke all those rules. It was a hot Jupiter, a gas giant bigger than Jupiter, orbiting ridiculously close to its star. So close that its year, the time it takes to go all the way around, is just 4 Earth days. 4. Monday to Thursday and back again. There are microwaved burritos with more chill than this planet. The funny part, it wasn't even the first exoplanet found. The actual first was even weirder. Back in 1992, astronomers Alexander Wolszczan and Dale Frail spotted something orbiting a pulsar, a rapidly spinning neutron star left over from a supernova explosion. These stars emit beams of radiation so regular they're sometimes used as cosmic timekeepers, and something was messing with one of them. They discovered not one but 2 planets orbiting the pulsar PSR B1257+12. Later, a third smaller one was added to the mix. You sit back stunned. The first planets we ever found were around a dead star. Talk about setting the bar weirdly high. It's like the first fish we discover in the ocean turns out to live inside a volcano and sing jazz. Historians still argue whether this discovery should count as the first true exoplanet detection. since a pulsar isn't exactly a sun-like star. But technicalities aside, the implications were staggering. If planets can survive or form again around a neutron star, then maybe they're more common than we ever imagined. Maybe planets aren't a rare fluke. Maybe they're just a regular part of star systems, like dust, comets, or that one forgotten screwdriver in your junk drawer. You imagine what life would be like on one of these first found exoplanets. Not comfortable. These planets likely endured the supernova that created their pulsar parent, which means they were either survivors of a stellar apocalypse or formed afterward from the wreckage. Both options are metal, literally. One of these planets, PSRB 1257 plus 12a, is thought to be about the size of the Moon, and it might be dense, like you drop your coffee and it leaves a crater dense. No atmosphere, no sunlight, just endless night punctuated by beams of radiation you really don't want to get caught in. Coziness? Zero. Survival chances? Nope. Real estate value? Currently trending downward. Still, the discovery taught astronomers a critical lesson. The universe doesn't follow Earth's rules. It doesn't care about our expectations. The cosmos is deeply uninterested in what makes us comfortable. It just is. After 51 Pegasi b was confirmed in the mid-90s, the exoplanet search exploded. At first, the finds were mostly gas giants close to their stars, because those are the easiest to detect. But slowly, as our instruments sharpened, we began to find smaller, rockier worlds. Planets that whispered, hey, I might be like Earth. Sort of, if you squint. Let's not pretend the early days were smooth sailing. There were false positives, rival teams, premature press releases, and a whole lot of, oops, that was a binary star. It was a bit of a science circus, and the audience, namely the public, was eager to believe we'd found Earth 2.0 every time someone's telescope hiccuped. A fun tidbit from those chaotic early days. In 1991, before the first pulsar planets were confirmed, a Canadian astronomer named Bruce Campbell and his colleagues almost discovered 51 Pegasi b using the radial velocity method. But their data was noisy, and they didn't trust it. So they held off publishing. Oof, that's got to sting. Imagine being the person who almost found the first alien world and decided, let's wait. Somewhere in the timeline there's a universe where they made history instead. You drift back into the broader picture now, watching as the exoplanet count climbs year by year. What was once fringe science becomes mainstream. Space agencies fund missions. Universities open planetary science departments. High schoolers run simulations of alien atmospheres. Exoplanets become dinner table conversation, if your dinner table is particularly nerdy. What changed wasn't just the discoveries, it was the mindset. We stopped asking, do other planets exist? And started asking, what kind of planets are out there? A subtle shift, but a profound one. It's like going from, are there fish in the sea, to, let's categorize them by how likely they are to stab us. And stab us they might. Some of these exoplanets are violent. Take HD 189733b, a gas giant so close to its star that temperatures hit over 1000 degrees Celsius. It rains glass, sideways. Imagine needing wipers that can handle high-velocity silica shards. That's not a vacation spot. It's a NASA PowerPoint cautionary tale. Others are more mysterious. There's GJ 1214b, a mini Neptune that might have an ocean hundreds of kilometers deep, with exotic forms of water like Ice 7, a type of ice that forms under extreme pressure and doesn't melt at normal boiling points. Basically, water that forgot how to water. These early discoveries made one thing clear. Earth isn't the model, it's an example, and maybe not a typical one. So now, as you drift back from those first unlikely planets, the cooked gas giants, the post-apocalyptic pulsar companions, the ones that rain glass and the ones that never see light, you begin to understand. We didn't just find planets, we found diversity, variation, cosmic weirdness, a menu of possibilities far more delicious than we could have imagined. The universe is not just sprinkling planets here and there, it's obsessed with them, and maybe, just maybe, one of them is looking back. You coast silently now in the shadow of a great mechanical eye, an enormous telescope in the cold vacuum of space, pointed unwaveringly at a tiny square patch of sky. It's 2009, and the Kepler Space Telescope is just opening its lens, ready to stare at 150,000 stars, and wait. Not spin, not scan, not wander, just wait. This mission is patience in orbit. the sort of deep, quiet watching that would drive most humans mad, but makes computers and astronomers absolutely giddy. The Kepler mission had one goal: to find Earth-like planets orbiting other stars. Not just big blimpy gas giants or planetary hellscapes, but small rocky worlds in the elusive habitable zone, that comfortable sweet spot around a star where liquid water could exist. Goldilocks territory, not too hot, not too cold, just right. Kepler worked using the transit method. You know the drill by now. Watch a star, wait for a planet to pass in front, catch the dip in brightness, do it again and again and again. If the dip happens regularly, congratulations, you've got a planet. If the dip varies, maybe 2 planets. If the dip is irregular, welcome to the delightful chaos of multi-planet systems, orbiting in weird resonances like badly programmed carousel horses. And Kepler found a lot. Over its 9-year mission, this one humble space telescope confirmed more than 2,600 exoplanets, with thousands more candidates still being examined. Suddenly the galaxy wasn't just a sea of lonely stars, it was full of planetary families, bustling and bizarre. One of the earliest major finds was Kepler 22b, located about 600 light-years away. This was big news in 2011. Kepler 22b was in the habitable zone. It was larger than Earth, so probably not very Earth-like in terms of gravity or atmosphere, but it was rocky, warm, and possibly wet. Headlines flew. "Earth's twin!" they shouted. Not quite. More like Earth's much bigger cousin with questionable furniture choices, but still a sign we were getting close. Kepler didn't just give us numbers, it gave us patterns. Before Kepler, we assumed our solar system was normal. Turns out, we're the weird neighbours with an oversized Jupiter parked way too far out back. Many of the systems Kepler found were packed tight with planets huddled close to their stars, like marshmallows melting near a campfire. Others orbited multiple stars. Think Tatooine sunsets, only way less romantic and way more unstable. One of the most iconic discoveries was Kepler 11, a star with 6 planets, all orbiting closer than Venus does to the Sun. These worlds were crammed together so tightly that you could stand on one and clearly see another planet in the sky. Huge and looming, like a second moon that forgot its manners. It was like watching a whole new genre of science fiction being written in real time. We weren't imagining planets anymore, we were cataloguing them. And the telescope, it was falling apart the whole time. In 2013, Kepler suffered a critical hardware failure. Its reaction wheels, those finely tuned gyroscopes used to aim the telescope, stopped working. With only 2 out of 4 wheels functioning, Kepler couldn't hold itself steady. Game over, right? Nope. NASA pulled off one of those, "why are you all so casual about this?" miracles and repurposed the telescope into a new mission, K2. By cleverly using solar radiation pressure to balance the telescope, they extended Kepler's life for another 4 years. It was like fixing a telescope with duct tape and math, and it worked. Under K2, Kepler kept finding planets. Smaller field of view, but the same unshakable mission. Stare at stars and find the shadows. The data Kepler collected was a dream, and a nightmare. Millions of light curves, rivers of data, signals buried in noise. Volunteers around the world joined in through platforms like Planet Hunters, looking for dips in brightness with their very human eyes. Sometimes crowdsourcing beat the algorithms. You gotta love a universe where office workers and school kids can find planets during lunch breaks. One particularly spicy example is KIC 8462852, a star whose light dimmed erratically and dramatically. Unlike your standard planet transit, this one flickered in chaotic, unpredictable ways. No clear pattern, no obvious explanation. Some scientists speculated dust clouds or comet swarms. The internet naturally leapt straight to alien megastructures. Historians still argue whether this was the best accidental marketing campaign for SETI, or just another case of wishful thinking disguised as science. Kepler changed everything. Before it launched, we knew of just a few dozen exoplanets. After, thousands! It shifted our sense of scale, permanently. Suddenly the idea that Earth was rare started looking pretty shaky. Here's your fringe tidbit. There's a theory that some of the planets Kepler found might not even orbit stars. They're called rogue planets, and they drift through the galaxy alone, unattached to any sun. Cold, dark wanderers. We can't confirm these easily. No star means no light to block, but gravitational micro-lensing hints they could be common. Imagine an entire planet, adrift in eternal night, its surface frozen solid, yet possibly warmed inside by radioactive decay or a molten core. Real estate ads for those places would say, remote location, stunning views, BYO star. Kepler's legacy isn't just about numbers, it's about proving that planets are a rule, not an exception, and that somewhere out there, maybe in the thousands of systems it quietly watched, is a world with blue oceans, white clouds, and the faintest possibility of life. You drift now away from the Kepler field, just a small patch of sky in the constellation Cygnus, barely the size of your hand held at arm's length. But in that tiny slice, over 2,600 planets, that's the real mindbender. If there are that many just there, how many more are hiding across the rest of the sky? You don't need to imagine alien life tonight. You don't even need to find Earth 2.0. It's enough to know that the galaxy is teeming with planets. Kepler taught us that we're not the exception. We're just early to the party. And the party? It's getting crowded. You hover now in a patch of galactic real estate where sunlight trickles gently onto planetary surfaces. Not too fierce, not too faint. This is the legendary Goldilocks zone, also known as the habitable zone. And while the name conjures up porridge and fairy tales, out here it's deadly serious. It's the difference between a world where water flows freely and one where it either boils off into space or freezes into eternal glaciers, a narrow strip of orbital safety. Earth is in it, Venus and Mars just outside, and beyond that, things get weird. The Goldilocks zone isn't the same everywhere. Around smaller, cooler stars like red dwarfs, it hugs the star tightly, so close that any potentially habitable planet might be tidally locked, showing one face to its sun forever, like the moon does to Earth. That means one hemisphere is stuck in a never-ending scorch, while the other lives in permanent night. You'd have to set up your alien vacation home right along the narrow twilight strip between day and night, a planetary no man's land where temperatures might be livable and the sunsets are eternally sideways. Around massive, hotter stars, the habitable zone lies farther out. But these stars don't live as long. Some burn out in a few 100 million years, not enough time for life as we know it to evolve. So even if a planet starts off with a perfect mix of warmth and water, the star might ghost it before it gets interesting. You hover beside a hypothetical planet. It's the right distance from a quiet, long-lived star. There's water in liquid form, a cozy mix of gases in the atmosphere, and the right amount of gravity to keep it all snug. You think, perfect, Earth 2.0, but then the devil in the detail starts whispering. Is the planet's orbit circular, or does it lurch wildly around its star like a drunken roller coaster? Does it have a magnetic field to protect its surface from stellar radiation, or is it being cooked alive slowly from above? Is there a moon to stabilize its tilt, or does it wobble like a spinning top on carpet, swinging between ice ages and heat waves every few centuries? Here's the sleepy catch. We don't know. Most of the time we can't know. Not yet. For all our fancy instruments, we still can't measure a lot of what makes a planet truly Earth-like. We can see its size, guess its mass, maybe sniff out the atmosphere from light passing through it. But does it have weather? Oceans? Tectonic plates? Cats? We're still in the dark. So much of the habitable planet business is based on assumptions, good ones, scientific ones. But assumptions all the same. Historians still argue whether defining habitability based on Earth is smart or myopically anthropocentric. After all, who says life has to want what we want? Here's a quirky fact to melt your mind. Earth itself wasn't always in the Goldilocks zone. The sun has slowly been getting brighter over billions of years, and early Earth, according to most models, should have been a frozen ice ball. But it wasn't. It had liquid water, early oceans, and probably squishy little microbes bubbling around. So what gives? This is known as the faint young sun paradox, and it remains one of science's favourite mysteries. Did Earth have a thicker, supercharged greenhouse atmosphere back then? Was the sun brighter than models predict? Did alien bacteria come pre-installed with thermal socks? No one agrees. But whatever the answer, it's a solid reminder that planets are complicated, and habitability is a moving target. You now find yourself perched mentally on the edge of a planet with a breathable atmosphere. Just barely. The mix of nitrogen, oxygen, trace gases, and maybe a hint of methane stirs around you. This is another variable we often oversimplify. Having water is nice. But breathable air? That's the real jackpot. And even that brings questions. Take Mars. Today, it's a dusty, dry, cold rock. But billions of years ago, it had rivers, lakes, and maybe even an ocean. The conditions were, briefly, perfect. Then the planet lost its magnetic field. The solar wind stripped away the atmosphere. The water escaped. The whole world went from potentially livable to utterly inhospitable because of one missing ingredient. It's like building a dream house, forgetting to install a roof, and then being surprised when it floods. So when we say a planet is in the habitable zone, what we really mean is, maybe if we're lucky, and if about 50 things go right, and also if the wind doesn't blow too hard. Here's where it gets dreamlike. Some scientists are now exploring the idea of subsurface habitability, places where life might exist underground, shielded from radiation and with heat provided by the planet's core. Moons like Europa or Enceladus in our own solar system are icy on the outside but may have warm oceans beneath. So maybe the Goldilocks zone is overrated. Maybe life doesn't care about sunshine at all. Maybe it prefers the dark, the cold, and the quiet press of stone and water. That redefines the whole exoplanet search. Suddenly, we don't just look at orbit and atmosphere, we start wondering about geology, tides, internal heat, and whether something squishy and weird is living peacefully a few kilometers below the surface, blissfully unaware of sunlight. Here's a fringe idea to tuck under your pillow. There might be planets with thick hydrogen atmospheres that trap heat so well they can support liquid water way outside the traditional habitable zone. These are called Hycean worlds, hydrogen-ocean hybrids, and they might host life in deep, warm oceans beneath swirling cloud banks. Imagine an entire planet covered in endless sea, its surface too hot for you, but perfect for some alien sea squish drifting along. You pause here, watching a star flicker softly in the dark, knowing that around it some anonymous planet may be playing the habitability lottery. Maybe it wins, maybe it loses. But the point is, planets keep trying. The galaxy keeps rolling the dice. The Goldilocks zone gives us a starting point, a way to prioritize the search. But you now understand it's just the top of the funnel, the beginning of a deeper mystery. Because habitability isn't just about distance, it's about context, planetary stories, geological histories, atmospheric whisperings, and a lot of things we can't yet measure. Still, when the light dims just right and the signal flickers, you allow yourself a moment of optimism. Maybe this one's the jackpot, maybe this one's just right. You find yourself pressed down by invisible weight now, your boots sinking slightly into the thick rocky crust of a world 5 times Earth's mass. The gravity tugs at your arms, makes your eyelids feel heavier, and your breath comes shallower. This is not Earth. This is a super-Earth, and just standing here is giving your knees trust issues. Super-Earths are planets that fall in between Earth and Neptune in size, bigger than our cozy blue ball, but smaller than a gas giant. They're not a specific category of planet type, they're a mass range, and that's what makes them so mysterious. Some might be scaled-up versions of Earth, with rugged continents and deep oceans. Others might be bloated mini-Neptunes with thick, crushing atmospheres and no surface to speak of. You'd need a submarine and an existential crisis to explore those. One of the best-known examples is 55 Cancri E. This super-Earth is about twice Earth's radius and orbits so close to its star that a year there lasts just 18 hours. The temperature's on its surface, over 2,000 degrees Celsius. That's hot enough to melt iron. Some researchers believe one side might be a vast ocean of lava. Others suggest it could have a diamond-like crust formed from carbon-rich materials. Either way, it's less second Earth and more first sauna in hell. The term super-Earth sounds exciting, like an upgrade. But don't be fooled. You wouldn't last long on most of them. High gravity alone causes a laundry list of problems. Your bones weaken faster, your heart works harder, and running feels like trying to sprint through molasses. You'd burn calories by the minute just existing. Still, there's reason to be intrigued. These planets are some of the most common types in the galaxy, and weirdly, we don't even have one in our own solar system. Historians still argue whether our lack of a super-Earth is a statistical fluke, or if something in our solar nursery prevented one from forming. Some theories even suggest that Jupiter's migration in the early solar system may have ejected or consumed a potential super-Earth. Thanks a lot, Jupiter. Many of the super-Earths we've discovered so far are found around red dwarf stars. These stars are smaller and cooler than our Sun but live for trillions of years, basically forever by human standards. Their habitable zones are closer in, and their planets often become tidally locked, with one side always facing the star. It makes for dramatic landscapes, perpetual day on one side, eternal night on the other, and possibly a twilight belt in between where life might flourish. You imagine walking across this twilight zone, where the sun hangs motionless at the horizon, casting eerie orange light that never moves. The wind whips from hot side to cold, stirring up storm systems that make Earth's hurricanes look like damp breezes. Rain? Maybe, but not of water. On some planets, it's molten iron. On others, glass. And in at least one case, scientists think it might rain rocks, solid, high-velocity rockfall, an exoplanet forecast straight from a video game glitch. Take Kepler 10c, a rocky super-Earth about 17 times Earth's mass. It was initially nicknamed the Mega-Earth. That's a lot of planet. But strangely, its size suggests it should be a gas giant. Instead, it appears to be mostly solid, a bouncer of a world with no chill and no squish. The surface gravity would make you feel like you were being pressed into the dirt by an angry elephant. If you tried to jump, you might manage a millimetre of airtime. Woohoo! Yet, there's fascination in this discomfort. Because if a planet is Earth-like in chemistry but scaled up in mass, it might still be habitable, just challenging. The thicker atmosphere could protect against radiation. The higher gravity might hold on to heat better. Life, if it exists, could be shorter, sturdier, stockier. Picture tree-trunk-legged lizards or deep-lunged insects the size of backpacks. Nature adapts. Life always has a way. A quirky theory worth whispering. Some researchers speculate that certain super-Earths might have water-world conditions, completely covered by global oceans hundreds of kilometers deep. No continents, no dry land, just an endless alien sea. Down below, high pressure might create exotic forms of ice, like Ice 7 or Ice 10, that don't melt even near the core. Above that, an ocean of unknown creatures perhaps. Not fish as we know them, but something else. Soft-bodied floaters, bioluminescent weavers. Imagine living in a world where dry is a myth passed down in squid folklore. But of course, the bigger the planet, the harder it is to launch things into orbit. Some scientists argue that intelligent life on a high-gravity world might struggle to ever develop spaceflight. The fuel demands scale up fast. They might never leave, or maybe they evolve in such a way that they never need to. Who's to say? Then there's the challenge of detection. Many super-Earths blur the line between rocky and gassy, just a bit more mass, and you start accumulating a thick hydrogen-helium envelope. That doesn't just mess with your chance of habitability, it messes with everything. The planet might look Earth-sized in radius, but its actual surface is buried under layers of high-pressure, high-temperature gas. Like Neptune got lazy and forgot to finish forming, one super-Earth, LHS 1140b, offers hope. It orbits a small red dwarf, has a radius about 1.7 times that of Earth, and sits comfortably in the star's habitable zone. It's likely rocky, and astronomers think it might have an atmosphere. If so, it could be one of the best candidates for further study with instruments like the James Webb Space Telescope. You cross your fingers. Maybe this one won't melt our face off. At the moment, we're still guessing. Our instruments are getting sharper, yes, but for now we're working with shadows and spectrums. Super-Earths remain elusive halfway points, too big to be familiar, too small to be easy to find, but they dominate the galaxy, and that matters. Because if these worlds are as common as they appear to be, then whatever kind of life the universe tends to produce, if any, might not be living on Earth-like planets at all. It might be living here, under heavy skies and stranger stars, adapting to pressures we can't survive and landscapes we can barely imagine. So you press your boot deeper into this imagined soil. The air is thick, the wind slow, the weight constant. This is not Earth, but it could still be home. You drift now in a system that defies everything tidy and logical about orbits. A massive, bloated gas giant, easily twice the size of Jupiter, swings around its host star at breakneck speed. You count the hours, not days, and realize its year lasts less than one Earth week. This is not a peaceful, distant world. This is a hot Jupiter, and it is chaos incarnate. Hot Jupiters were the first exoplanets we spotted with the radial velocity method, and that wasn't an accident. Their size and speed made them stick out in the data like someone shouting in a library. But they were also not what anyone expected to find. Big gas giants? Sure. Gas giants orbiting their stars closer than Mercury, faster than a space tick-tock trend? That felt impossible. You land conceptually in the upper atmosphere of one of these giants. Let's call it WASP-76b, because astronomers never miss a chance to name a planet like it's a password. The temperature here is over 2,400 degrees Celsius. Iron vapor exists in the sky, and scientists believe that it rains molten iron on the night side. Yes, metal rain. You're going to need a much tougher umbrella. This isn't the distant icy kind of gas giant you're used to from Jupiter or Saturn. Hot Jupiters are tightrope walkers, whipped around their stars so closely that they're often tidally locked, with one face always sunward. The heat difference between day and night is so extreme that winds may reach speeds of thousands of kilometers per hour, redistributing heat in a constant scorching cyclone. And yet, these planets exist in absurd numbers. We've found hundreds of them. Some orbit their stars in less than 2 Earth days. That's not a calendar, that's a pizza delivery window. The real question that made astronomers sweat back in the early 2000s was, how did they get there? Planets shouldn't form that close to their stars. The heat is too intense, the material too sparse. Gas giants are thought to form much farther out, where it's cool enough for gas to condense and clump together. So hot Jupiters, they didn't start there, they migrated. You picture it like a cosmic traffic jam. Giant planets form way out, then slowly spiral inward over millions of years, either through gravitational interactions with the protoplanetary disk, or by bumping into other planets like a drunk at a house party. Some crash into the star, others settle into scorching tight orbits. Hot Jupiters are the survivors, the ones that got too close and just stayed. This planetary migration throws all your nice tidy models into a blender. You thought solar systems formed like ours? With rocky planets close in, gas giants farther out, and icy stuff at the edge? Think again. Hot Jupiters rewrite the script. They barge through early systems like bulldozers, potentially scattering smaller planets, or flinging them out entirely. Any Earth-like world that might have existed in the habitable zone probably got evicted. Historians still argue whether this kind of migration happens in every system, or if we're just better at spotting hot Jupiters because they're big, bright, and close to their stars. It's possible they're just easier to find, not necessarily more common. But even if they're rare, their very existence means that the early life of a planetary system might be a lot more smashy. Here's a quirky fringe idea for your sleepy side thoughts. Some hot Jupiters may have stripped cores, once gaseous giants that got so close to their star, the outer layers of atmosphere blew away, leaving behind a rocky metallic skeleton. Like cosmic scarecrows. It's an eerie image, a dead gas giant's core, still orbiting, still hot, a ghost of its former self. Then there are the puffy hot Jupiters, planets like HATP-67b that are so close to their stars and so hot, their atmospheres have expanded into bizarre balloon-like shapes. They're low density. Imagine a world larger than Jupiter but lighter than cotton candy. The kind of planet where you could jump out of a spaceship and just kind of bounce, probably once. You turn your attention to HD 209458b, also known as Osiris. This was the first exoplanet where we observed an atmosphere being blown off into space, a long tail of hydrogen trailing behind it like a comet. It's being stripped atom by atom by the intense radiation of its star, poetic in a doomed kind of way. Despite the chaos, hot Jupiters are useful. Their size and proximity make them ideal targets for atmospheric studies. Astronomers can analyse starlight as it passes through their atmospheres during transits, teasing out the chemical composition. We've found sodium, potassium, water vapour, carbon monoxide, and more. Not life, of course, but clues. Practice. These giant planets are the gateway drug of exoplanet science. They also provide a strange kind of planetary drama. Take Corot 2b, which is orbiting a star so active, the planet might be shrinking under the assault. The star blasts it with X-rays and flares, possibly altering its structure in real time. Watching this planet is like watching a reality show where the cast is melting. Then there's WASP-12b, a planet so close to its star that it's being distorted into an egg shape by gravitational forces. Astronomers believe it's slowly spiraling inward and will eventually be devoured by the star. Give it 10 million years or so, a quick bite. So you hover in this cosmic neighborhood, full of bloated, burning giants and their slow, chaotic deaths. The skies here are not blue, the sunsets are not gentle, but the science is rich. Because every hot Jupiter we find, every weirdo orbit, every puffed-up atmosphere and molten iron cloud challenges our assumptions. Reminds us that planets are not neatly ordered marbles spinning around politely glowing stars. They are restless, they move, they collide, they warp and stretch and adapt. And even in the violence there's beauty. You turn slowly, watching one more gas giant race across its tiny orbit, its bloated form glowing faintly in the star's relentless light. A world forever running in place, forever on fire. You won't find Earth here, but you will find answers. You ease into orbit now around a dim red star, a fraction the size of our sun but incredibly stable, incredibly long-lived. It's not flashy, it doesn't radiate warmth the way Sol does, but it does something far more exciting. It hosts a family, 7 known planets to be precise, all rocky, all tightly packed, and at least 3 in the habitable zone. You're looking at the famous and very sleepy-sounding TRAPPIST-1 system. Nestled just 40 light-years away, TRAPPIST-1 is practically next door in galactic terms. If the Milky Way were a city, this system would be a couple neighborhoods over, just beyond the pizza place with questionable hygiene. Close enough to matter. And yet, when astronomers first found it, it felt like science fiction. 7 Earth-sized planets orbiting a single ultra-cool red dwarf star. You can barely get 7 houseplants to survive the same conditions, but here they are in a delicate gravitational dance, a miniature planetary ballet. TRAPPIST-1's star is so dim that you could stand on any of its planets and see the sun as a small red disk in the sky. Much larger than our sun appears from Earth, but way duller. A constant rust-coloured glow. Warm but never harsh. You'd never need sunscreen here, though you might need radiation shielding. Let's take a slow stroll through this cosmic family. The planets are named with classic scientific flair, from TRAPPIST-1b to TRAPPIST-1h. All of them are roughly Earth-sized, all orbit within a distance that would fit comfortably inside Mercury's orbit. That's right, 7 planets crammed into a space smaller than one tiny orbit in our system. If this were your apartment building, you'd hear everything through the walls. But that's what makes the system so thrilling. The planets are so close together that from the surface of one, another might appear bigger than our moon. Imagine standing under a lavender sky and seeing a neighbouring world hanging above you like a second Earth, trailing clouds and maybe even weather. No telescope needed, just eyes. You float now above TRAPPIST-1e, the superstar of the group. It's firmly within the habitable zone, thought to have a rocky surface and maybe even liquid water. Its density is similar to Earth's. If we had to nominate a second Earth candidate today, this one would make the shortlist. Astronomers get misty-eyed just thinking about it. Still, don't pack your bags just yet. Red dwarf stars like TRAPPIST. One may be stable long-term, but they're also flare-prone, especially when they're young. Scientists think that powerful ultraviolet flares could strip away a planet's atmosphere, or worse, prevent one from forming at all. So, while TRAPPIST-1e could be habitable, there's a strong chance it's been flash-fried into sterility. Historians still argue whether red dwarf planets can hold on to their atmospheres at all. Some models say yes, if the planet has a strong magnetic field, if it formed early enough, if it kept its water tucked safely underground or beneath thick clouds. Lots of ifs. And in space, if is doing a lot of heavy lifting. Still, the TRAPPIST system gave scientists something precious: hope through proximity. It's close enough that telescopes like James Webb can study it in detail, right now. In fact, we've already begun. JWST is sniffing the atmospheres of these planets by measuring how starlight filters through them during transits. We're looking for signs of water vapour, methane, carbon dioxide, chemicals that could hint at biological processes, or at least make for decent weather reports. So far the results are inconclusive. Some planets might have thin atmospheres, others maybe none at all. But we're getting better, and each pass gives us more data, more clarity, and more reason to keep watching. Here's a quirky fact to lull you into wonder. The TRAPPIST-1 planets are in orbital resonance. That means their orbits are mathematically linked in a beautiful cosmic rhythm. For every 2 orbits one planet makes, another might make 3. It's like the whole system is choreographed by a quiet, persistent metronome. This resonance also stabilizes the system. Gravitationally speaking, it helps the planets avoid smashing into each other, which is nice. Imagine 7 planets constantly playing gravitational bumper cars. Not exactly ideal for maintaining a biosphere. And the namesake, TRAPPIST, stands for Transiting Planets and Planetesimal Small Telescope, a Belgian observatory that first detected the system. Yes, it's a nod to Trappist beer, which is both charming and extremely on-brand for European astronomers. Somewhere out there, a planet-hunting telescope is raising a frosty glass to its interstellar discoveries. You picture the entire TRAPPIST-1 system like a snow globe. Compact, colourful, spinning slowly under that red starlight. 7 rocky worlds, each with their own secrets. Some dry, some scorched. Maybe 1 or 2 just right. You lean in, breath held, waiting for signs of clouds, weather, oceans. Anything familiar. But familiarity might be beside the point. These are alien worlds. Their atmospheres might smell of sulfur or ammonia. Their clouds could be methane. Their oceans, if they exist, might be acidic or filled with exotic life unlike anything we know. The laws of chemistry still apply, but biology's always been the wild card. And what if we did find life here? Microscopic, probably. Maybe just biosignatures, chemical hints in the atmosphere that can't be explained by geology alone. That alone would rewrite everything. We wouldn't be alone. Earth wouldn't be unique. TRAPPIST. One dares you to dream. 7 planets, 7 experiments in planetary chemistry, 7 chances at life, or 7 long silences echoing in red light. You float a little closer to TRAPPIST-1e now. You press your thoughts gently to its surface, to its imagined shores and skies. You don't hear music, you don't hear chatter, but you do hear potential. In the soft twilight of this distant sun, life could still be hiding. Deep underground, beneath ice, in acid pools, or in oceans so still and dark we'd never detect them without diving in ourselves. So you drift gently now, out past the last of the TRAPPIST T1 planets. 7 little rocks huddled close to a tired red star, humming a silent lullaby across space. They may never speak. But we're listening. You float now in deep interstellar silence, surrounded not by stars or planets, but by data. Thin, meticulous streams of numbers that trickle from telescopes across the world and orbiting in space. You watch as light, ancient, delicate, and filtered through countless miles of vacuum, hits a mirror, splits into a rainbow, and reveals a planet. Or at least the faint hope of one. You've reached the next level in the great cosmic treasure hunt, trying to find another pale blue dot, a true Earth twin. And to do that, you need more than just size and orbit. You need to read its colour. This is the realm of photometric fingerprinting, where astronomers look at the colour of light reflected by exoplanets to infer their surface and atmospheric conditions. It sounds simple, it's not. You're trying to detect a planet's glow, its reflected light, while it's drowning in the overwhelming brightness of its parent star. It's like trying to photograph a lightning bug next to a lighthouse from across an ocean, while sneezing. And yet somehow it works. It starts with something called the planetary albedo, how much light a planet reflects. Earth reflects about 30% of the sunlight it receives. Venus? Almost 70%, it's covered in bright clouds. A snowball planet, even more. A lava world, practically none. By measuring the slight change in total brightness of a star-planet system as the planet orbits, astronomers can infer the colour and reflectivity of the planet. From there, the detective work begins. A planet that reflects more blue light might have oceans or Rayleigh scattering atmospheres like ours. One that leans red or grey might be dusty, barren or clouded with methane. This is where algorithms step in, the quiet heroes of exoplanet research. Sophisticated AI and statistical models comb through these light signatures, looking for patterns that human eyes could never spot. They're trained on Earth-like conditions, taught to recognise the subtle colour palette of habitability. One especially poetic technique is called multiband photometry. It involves measuring the light from a planet in multiple wavelengths, like taking a photo with different colour filters, and then using that to reconstruct a basic colour profile Earth. When viewed this way, looks bluish-green with hints of white. It's a unique spectral fingerprint. Astronomers have used this to create simulated colour maps of Earth from afar, then fed those simulations into AI to train it on what to look for in distant systems. You're essentially teaching machines to dream of Earth. A quirky little tidbit. Scientists once tried to simulate what Earth would look like to aliens. They pointed a telescope at the moon during a lunar eclipse and observed sunlight that had passed through Earth's atmosphere and reflected off the moon. In that faint coppery glow, they detected ozone, water vapour, and even signs of vegetation. It was the ultimate reverse selfie. This technique is now being reverse engineered to study exoplanets. We look for similar signals, biosignature bands, in the light filtering through their atmospheres. It's like trying to smell dinner from 5 blocks away and guess what's on the menu. Difficult, but not impossible. Some of the most promising tools for this are still being built. One of the most anticipated is the Nancy Grace Roman Space Telescope, which will carry a coronagraph so precise it can block out the blinding light of a star to image nearby exoplanets directly. And when it does, we might finally catch a glimpse. Not just a squiggle on a chart, but a real dot of colour in the vastness of space. A second Earth, maybe. Historians still argue whether the idea of finding Earth 2.0 is good science or just a romantic obsession. After all, planets don't have to look like Earth to support life. But there's something deeply human about it. We aren't just looking for any life, we're looking for life that looks back. So here's how it might go. One day, a telescope picks up a faint flicker, a drop in starlight that repeats like clockwork. We calculate the orbit, the size, it's in the habitable zone. We turn other instruments toward it. We measure the light, it's bluish, with scattered white, a strong ozone line, a bump in the chlorophyll region, some methane, some oxygen. And then we sit there, stunned, because that signature is us. That's Earth's fingerprint, but on a planet 50 light-years away. Is it life? We won't know, not for a long time. But that colour, that flicker, that chemical bouquet, that's what Earth would look like from the stars. Of course, there are false alarms. Planets with similar compositions but no life. Planets with weird clouds that trick the sensors. One time, researchers got excited about a planet that turned out to be a background star. Another was a processing error. In one case, the signal came from the edge of the telescope's lens, a literal glitch in the hardware. Imagine mistaking a smudge for salvation. Still, every step gets us closer. The faint blue dot algorithm isn't one algorithm, it's a whole class of tools. Tools that are being refined daily, by students, by amateurs, by AI. There's even talk of future space interferometers, made of multiple spacecraft flying in precise formation, that could combine their light to create high-resolution images of exoplanets. It's like building a zoom lens the size of a small city, for one picture. And all of this effort, for what? A blurry dot, a tiny dip in brightness, a pale smudge of reflected starlight. But that smudge could be someone else's sky, someone else's ocean, someone else's home, or perhaps just the hope of it. So you sit back now, letting the data wash over you, watching light curves blink across screens, listening to spectral lines hum in invisible wavelengths. The silence of space becomes symphonic, not empty, but subtle. And somewhere in that whisper, Earth's twin might be waiting. A planet just the right size, just the right colour, glowing softly in borrowed light, casting its story across the void. You wouldn't see trees, you wouldn't see cities, but you might see green, you might see water, you might see possibility, and that's enough to keep searching. You're floating now just above the clouds of an alien sky, not Earth's, not even close. The air here is thick, roiling with foreign gases, and the colour of the sky isn't blue. It's a murky green, or maybe a burnt orange, depending on where the sun sits. You can't breathe it, you can't smell it, but with the right instruments, you can read it. This is the frontier of exoplanet exploration, atmospheric analysis, the science of sniffing alien skies from light years away. It sounds ridiculous. You're not sending a probe, you're not scooping up samples, you're just collecting the faint light from a distant star as it passes through a thin sliver of a planet's atmosphere. And from that, you can tell what's in the air. Magic? Number. Just physics. Really, really fancy physics. This trick is called transmission spectroscopy, and it works like this. When a planet transits its star, that is, crosses in front of it from our perspective, it blocks some of the star's light point of view. Some of the starlight passes through the planet's atmosphere. Gases in the atmosphere absorb specific wavelengths of light. So by comparing the star's light during the transit to its light when the planet isn't in the way, scientists can spot the missing wavelengths and figure out what chemicals are present. You're not seeing an atmosphere, you're decoding it. And what have we found so far? Water vapour, carbon dioxide, methane, hydrogen, sodium, potassium, even helium, trailing off in long comet-like tails from overheated planets. In a few cases, carbon monoxide, which, fun fact, isn't great for breathing, but does tell us something about a planet's formation and evolution. Each of these molecules leaves a kind of fingerprint in the spectrum, like little whispers of chemistry from across the void. One of the first breakthroughs came with HD 209458b, a hot Jupiter nicknamed Osiris. Yes, like the Egyptian god. It was the first exoplanet where an atmosphere was detected, specifically sodium, followed by hints of hydrogen and oxygen. The planet's outer atmosphere is escaping into space, stripped away by solar radiation. It's not habitable, obviously, but it was a huge proof of concept. Alien skies could be read, and we've gotten better at it since. Much better. Enter the James Webb Space Telescope, which isn't just pointing its golden mirrors at galaxies and nebulae, it's also sniffing exoplanet atmospheres with the enthusiasm of a bloodhound in a bacon factory. Webb's infrared instruments are sensitive enough to pick out the faintest spectral features in light passing through atmospheres, even from small rocky worlds like TRAPPIST-1b and E. Have we found life yet? Number. But we're getting awfully good at ruling things out. For example, Webb recently observed TRAPPIST-1b and found no evidence of a thick hydrogen-rich atmosphere, which is actually good news. It means the planet is likely rocky and might have retained a thinner, more Earth-like atmosphere. Maybe, if it hasn't been blasted away by stellar flares. You know, space problems. Historians still argue whether the presence of molecules like oxygen or methane can be considered definitive biosignatures. After all, abiotic processes, non-living ones, can produce these gases too. Volcanoes, lightning, UV radiation, and photochemical reactions can all stir up these chemicals. It's the context that matters. On Earth, for example, methane and oxygen exist together because life keeps replenishing them. Without biology, they cancel each other out fairly quickly. So the dream is to find a planet with a disequilibrium atmosphere, where certain gases shouldn't coexist unless something's actively producing them. Like finding smoke and thinking, okay, where's the fire? You can think of this as searching for alien flatulence, by the way. Yes, some of the best biosignature targets involve gases like methane, which on Earth often comes from cows. Somewhere in a telescope proposal, a very serious astronomer has probably typed the phrase potential biosignatures from biological outgassing. Delightful. But even beyond biosignatures, atmospheres tell us so much. About climate, about pressure, about heat distribution. We've found planets with super-rotating winds, where the atmosphere whips around the planet faster than the planet rotates. Others have temperature inversions, like Earth's stratosphere, but flipped, hot above and cool below. Some are likely completely cloud-covered, others clear as glass. A strange little tidbit. On GJ 1214b, a mini Neptune about 48 light-years away, observations suggest an atmosphere made of water-rich vapour or high clouds of unknown composition. Scientists still haven't figured out exactly what the clouds are. They might be salt, or sulphur, or something we've never seen before. It's like trying to do a weather forecast for a planet where it might rain steam or pebbles. We've also started analysing emission spectra. That's when we look at the heat given off by a planet, rather than the light passing through it. On tidally locked planets, for instance, you can use this method to compare the temperature of the day side versus the night side. If there's a big difference, maybe the atmosphere isn't distributing heat well. If it's more even, maybe there's wind, weather, circulation. Maybe it's alive in its own way, but it's not all infrared beauty and carbon chemistry. Some planets, total mystery, flat lines in the data, nothing to see here, just a dark rock with no atmosphere at all, or one so thick and opaque that no light gets through. Some of these planets absorb nearly all the light that hits them. They are the true black holes of planetary personality, utterly unwilling to share their secrets. Still, each one we analyse, each atmosphere we pass, adds a brushstroke to the big picture. We're not just cataloguing planets, We're building a weather report for the galaxy, mapping atmospheres across light years, comparing pressure systems and wind speeds and cloud formations of worlds no one will ever walk on. Yet. Because one day, we might. And when we do, we'll already know what the sky is made of, whether the clouds will melt our bones, whether we need a pressure suit or just a really good pair of sunglasses. You watch as one more planet crosses its star, the light dims, just slightly, just enough. The atmosphere whispers its story through a filter of science and starlight, and you lean in. You drift now across a shortlist. Not a cosmic one this time, not all the stars and planets ever, but a carefully curated collection. These are the current best contenders, the maybe Earths, the second homes. These are the planets that when astronomers look at the data, they hesitate, just for a moment, and wonder if we might have found something close. Of course, it's still early. These aren't confirmations, you won't be booking a flight, but they're tantalizing, and they hint, more than any equation ever could, that Earth might not be the only habitable game in town. First up, Kepler 452b. Ah yes, the media darling. When NASA announced this one back in 2015, the headlines went wild. Earth 2.0 discovered. Our twin is real. The planet orbits a G-type star, just like our Sun, and it's smack in the middle of that oh-so-marketable habitable zone. 1 year there, about 385 Earth days. Nice. Predictable. The catch. It's 1.6 times Earth's radius, which probably makes it a super-Earth, and that means its gravity might be, well, less romantic. Your bones would complain, your muscles would revolt, lifting a coffee mug might require teamwork. Still, Kepler 452b checks so many boxes that it's hard not to feel a little flutter. Same kind of star, same kind of orbit, possibly rocky, possibly cloudy, possibly not empty. Then there's Kepler 186f, a smaller, quieter star system, with a planet that's just 10% larger than Earth. It sits near the outer edge of its star's habitable zone. A bit chillier, sure, you might need a thicker coat, but its star is a red dwarf, which means it's cooler and smaller than the Sun, but also potentially dangerous in its youth thanks to flares. The light would look dimmer, redder. The sky might be twilight blue all day long. Not a bad mood, honestly. Scientists still argue whether red dwarf planets can hold on to atmospheres after their early years of radiation trauma. Some say yes, with enough magnetic shielding. Others think the solar flares would just strip everything away like a cosmic leaf blower. Kepler 186f remains stubbornly quiet on the matter. Next on the tour, LHS 1140b. You remember this one from earlier, the rocky super-Earth in the habitable zone of a calm red dwarf. What makes this one special is its density. It's heavy, rock solid, and that might mean it has a thick atmosphere, something we could study with Webb or future missions. It's also relatively close to Earth, only about 40 light-years away. That's practically a neighbour, galactically speaking. If we ever send interstellar probes, this one's high on the list. And then we have Proxima Centauri b. Ah yes, the closest potentially habitable planet we've ever found. Just 4.2 light-years away, orbiting the nearest star to our Sun. Sounds perfect, right? Well, not quite. It orbits a flare-happy red dwarf, Proxima Centauri, and it does so in just 11 Earth days. That's fast. It's likely tidally locked, and those flares, they could sterilize the surface unless the planet has some seriously hardcore protection. Still, it's there, close, real. And scientists have even begun speculating about sending probes, tiny spacecraft riding lasers, to visit it within a human lifetime. You pause to appreciate the absurdity. We might not be that far from launching interstellar postage stamps toward a potentially habitable planet. If that doesn't make your inner sci-fi fan roll over in delight, nothing will. A quirky, under-the-radar candidate, Teegarden's Star B. Yes, that's the actual name. It's orbiting a red dwarf just 12 light-years away and seems to be almost Earth-sized, almost Earth-massed, and sitting right in the Goldilocks zone. What's unusual is that we found it using the radial velocity method, not the more common transit method. That means we haven't seen it cross in front of its star, so we can't study the atmosphere yet. But we can feel it tug. A little gravitational nudge in the numbers. It's shy, but it's there. Meanwhile, you float by TOI 700d, a more recent find from the TESS mission. It's about 100 light-years away, Earth-sized, and in the habitable zone. The star is a quiet red dwarf, the planet gets a moderate amount of radiation. It could have an atmosphere. It could have water. It could be your next summer home, assuming you enjoy spending 100 years commuting each way. Of course, none of these are confirmed Earth twins. At best, they're Earth cousins. You'd recognise the family resemblance, but probably struggle at dinner. Different air, different light, different history. Still, one stands out. Kepler 442b. It's about 1,200 light-years away, around a K-type star, less hot than the Sun, more mellow than a red dwarf. The planet is about 1.3 times Earth's size and firmly in the habitable zone. Its star is stable, the orbit's good, the gravity's manageable. We haven't studied its atmosphere yet, but on paper? This one's quietly climbing to the top of the charts. Here's your quirky tidbit of the evening. Some scientists, when building models of potential habitability, use a ranking system called the Earth Similarity Index, ESI. It compares things like radius, density, temperature, and orbital characteristics. Earth, of course, scores a perfect 1.0. Some of these planets score between 0.8 and 0.9. That's like getting a B+ on your cosmic report card. Not perfect, but good enough to ask out for coffee. But the ESI isn't everything. It doesn't factor in atmospheric composition, magnetic fields, volcanic activity, or tectonics, all things that can make or break habitability. You can have the right mass, right orbit, right star, and still end up with a lifeless rock. Just ask Mars or Venus. Great resumes, terrible interviews. So what does it all mean? You float now above this quiet list, these quiet maybes, and you realise this isn't just science, it's longing. Every new planet added to the list is a kind of love letter to the future, a whisper of, you're not alone, you might have options. And with every discovery, our definition of Earth-like expands. We learn to expect weirdness, to welcome variety, to imagine life not just on blue-green twins but on purple cloud worlds, red-skied lava oceans and deep-sea alien Earths where the sun never rises. These candidates, this best-of list, it isn't definitive. It will change. Some will be downgraded, others upgraded. New missions will peer deeper, AI will catch signals we missed. The dots will get sharper, the stories will become clearer, but tonight, just for now, let yourself imagine standing on a distant shore, looking up at a star that's not the sun, breathing air you shouldn't be able to breathe, and hearing something, wind maybe, rustling in alien trees. The second Earth is out there. We just haven't quite shaken hands yet. You drift now above a shimmering web of glass and gold, floating 1,000,000 miles from Earth, sunshield extended like a cosmic parasol. This isn't a sci-fi movie prop. It's one of the most powerful tools ever built by humans, a space telescope, and it's staring deep into the cosmos with the quiet intensity of a librarian who's had enough of your talking. These are the planet hunters, the instruments that gave us everything we know about exoplanets, and the ones that will take us further still. The first hero in this skyward saga was Hubble, launched in 1990 and designed primarily for deep space imaging. But somewhere along the way, clever scientists realised it could also detect tiny dips in light, planetary transits, and analyse atmospheric spectra. Hubble was never supposed to hunt exoplanets, and yet it helped us confirm the first atmosphere on one. It was like giving your old car a jet engine and finding out it could moonlight as a racehorse. Next came Kepler, which you've already met, a masterclass in patience and pixel counting. Kepler didn't move, it just stared at a patch of sky and counted blinks. But with that relentless focus, it rewrote the map of the galaxy. The sky went from a quiet wallpaper to a buzzing jungle of planets. Some estimates suggest that up to 1 in 5 sun-like stars could host an Earth-sized planet in the habitable zone. Kepler gave us numbers, and those numbers told us we're not special, which ironically is kind of special. When Kepler lost 2 of its stabilizing wheels, NASA could have let it drift gently into the night. But no, enter K2, the mission sequel no one expected. Engineers used the pressure of sunlight to help steer the wounded telescope, letting it scan along the ecliptic plane. It discovered more planets in that second life. Honestly, it deserved a sitcom. Then came the eager successor, TESS, the Transiting Exoplanet Survey Satellite. TESS doesn't stare at one patch. It scans the entire sky, sector by sector, looking for planets around bright nearby stars, the kind we can follow up on, poke and prod with other instruments. TSS is less about quantity, more about quality. These are the targets we can dream of studying in detail. And now, standing at the top of the observational food chain, we have the James Webb Space Telescope. Big, golden, cold and complicated, Webb can see in the infrared, perfect for detecting the chemical fingerprints in exoplanet atmospheres. Its instruments are so sensitive they can pick out heat signatures from a planet hundreds of light years away, using just the faintest starlight that passes through its upper atmosphere. Already, Webb has begun analysing exoplanets like WASP-39b, detecting carbon dioxide and hints of cloud structure. For the first time, we're not just finding planets, we're characterising them, peeling back layers, reading their weather, even, perhaps one day, catching a glimpse of biosignatures, chemical clues of life. Historians still argue whether Webb will be the telescope that finds alien life. Some say yes. If life is common, Webb will see hints of it. Others say no. It's still too early, our instruments too blunt, the distance is too great. But the fact that it's even a question we're seriously asking tells you how far we've come. But wait, there's more. Coming soon to a launch pad near you is the Nancy Grace Roman Space Telescope. Previously known as WFIRST, Roman will feature a coronagraph, a device that blocks out a star's light to directly image its orbiting planets. This isn't about watching light flicker. This is about actually seeing other worlds as faint points of light next to their parent stars. Roman will give us the closest thing we've ever had to direct exoplanet portraits. You float between these instruments now, each a mechanical eye in the void, each peering into the dark with obsessive precision. Some are in orbit, some are earthbound, like the powerful ESO's Very Large Telescope in Chile, or Gemini and Subaru. These ground-based observatories, equipped with adaptive optics, can correct for Earth's atmospheric distortion in real time, like putting glasses on the Earth. And the clarity is astonishing. Some astronomers are dreaming even bigger, literally. Plans are already underway for telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, which, true to their creatively bland names, will have absolutely massive mirrors capable of incredible detail. These monsters will resolve distant starlight down to the subtlest of details, possibly imaging Earth-like planets directly. One fringe idea gaining traction is the starshade, a giant flower-shaped disk that would fly thousands of kilometers in front of a space telescope, blocking starlight and allowing direct imaging of planets. Imagine launching a floating umbrella the size of a baseball diamond just to block out the sun enough to see a tiny orbiting dot. The precision needed is absurd, the ambition even more so. And then there's Le Voir, a concept for a multi-wavelength, ultra-powerful telescope that could one day catalogue thousands of Earth-sized planets, measure their atmospheres, and even determine surface features. Le Voir isn't funded yet. It may never fly. But its blueprints are enough to make your jaw drop. Think of it as Webb's much beefier, much more extroverted cousin. Even now, AI and machine learning are being used to reanalyze old telescope data, finding missed planets in the noise. Yes, we've trained software to go back and clean up our homework, and it's doing surprisingly well. Here's a strange little tidbit to tuck under your pillow. A team of astronomers once found a planet by measuring the tiny gravitational tug it exerted on another planet, not the star. That's how sensitive our instruments are getting. We're now watching planets tug on each other from across the light years. The more eyes we build, the more we see. And with each new mission, we learn not just where planets are, but what they are, what they're made of, how they behave, and maybe whether they're inhabited. You lean back now, watching the sky from this perspective. Not with your eyes, but through the lenses of a dozen instruments, each tuned to a different kind of truth. The sky isn't empty. It's full of tiny flickers, quiet shadows, and faint whispering signals. It's a treasure map written in photons. And the telescopes, they're the translators. You drift now through a cloud, not of gas, not of dust, but of pure human imagination. You've stepped beyond data, beyond algorithms, and into the dream world where numbers become narratives. This is the realm of science fiction, where exoplanets have always existed, even before science caught up to them. You're no longer orbiting known stars. Tonight, you're drifting through fictional constellations, worlds imagined, drawn, painted, and built long before any telescope saw a real one. We've always been dreaming of other Earths. In 1516, Thomas More imagined utopia, not a planet but a fictional island that hinted at perfect society in an unreachable place. Centuries later, as astronomy grew teeth, writers started aiming their utopias skyward. By the 19th century, we were already imagining life on Mars, Venus, and even the Moon. H.G. Wells gave us Martians. Edgar Rice Burroughs gave us Barsoom. These weren't scientifically accurate, but they were emotionally right. We wanted neighbours. Jump ahead a few decades and the floodgates open. The moment real spaceflight entered the conversation, fictional worlds exploded. Star Trek, Star Wars, Dune, Doctor Who, each offered galaxies teeming with planets. Different climates, cultures, species. Planets as metaphors. Planets as settings for morality plays, action set pieces, and occasionally, diplomatic disasters over poorly translated greetings. Think of Tatooine, Luke Skywalker's dusty homeworld. Its twin suns set the tone immediately. This is not Earth. But here's the twist. Tatooine-style planets are real. We've found exoplanets orbiting binary stars, including one in the Kepler-47 system, with a stable, multi-year orbit around two suns. Science fiction didn't just guess right, it predicted. Or take the infamous Mustafar, where the lava never stops flowing. Fictional? Yes. But eerily close to planets like 55 Cancri, where the surface may be a molten nightmare, and K2141b, where it literally rains rocks and has a magma ocean. Mustafar would feel right at home in the Kepler catalogue. Then there's Arrakis, from Dune, a planet of sand, spice, and absurdly valuable worms. While the economics are a bit speculative, desert planets, totally plausible. Scientists have already found planets likely to be hot, dry, and stripped of moisture, especially those close to small stars. Could they host life? Harder to say. But science is inching closer to what Herbert wrote decades ago. You hover now above Pandora, the bioluminescent paradise from Avatar, a moon orbiting a gas giant teeming with life. Fictional, yes, but conceptually, solid. Some of our most intriguing possibilities for habitability aren't even on planets, they're on moons. Think of Europa, Titan, Enceladus, all orbiting gas giants, all icy, all strange, and all possibly hiding life. A large enough moon orbiting an exoplanet might have tidal heating, a thick atmosphere, and a cosy little ecosystem going, without ever needing a habitable zone star. Historians still argue whether science fiction truly predicts the future, or simply inspires the people who build it. Probably both. There's a strange feedback loop. Artists imagine something wild, scientists take it seriously, engineers make it real, and then artists go even further. Rinse and repeat until someone launches a warp drive by accident. Here's a fun tidbit to add to your dreams tonight. In the 1990s, a physicist named Geoffrey Landis, also a science fiction writer, proposed a habitable zone on Venus not on the surface, but in the clouds. At about 50 kilometers up, the temperature and pressure become Earth-like. Theoretically, humans could live in floating balloon cities suspended in Venus's atmosphere. Fiction? Maybe. But the math checks out. That same imagination is now being used to model exoplanets. Astrobiologists regularly consult sci-fi writers. NASA has hired artists to visualize alien ecosystems. Climate modelers use fictional data to simulate weather on planets that don't exist. Yet. The lines are blurring. Even video games have joined in. Mass Effect, No Man's Sky, Outer Wilds, each presents exoplanets not just as backdrops, but as places with depth, physics, ecosystems. These games have quietly educated a generation of players on orbital mechanics, atmospheric chemistry, and what a planet feels like to walk across. They've done what textbooks can't, made the unknown feel familiar. But here's the quiet truth hiding under all the fiction. No matter how exotic these worlds are, they're usually just mirrors. Tatooine is about loneliness. Arrakis is about politics and survival. Pandora is about connection. Even Earth-like exoplanets in sci-fi often serve to explore human themes: identity, society, mortality. The planets aren't the point. We are. And yet, sometimes, fiction gets scarily close to science. Carl Sagan's pale blue dot wasn't just poetry. It was the vision. A planet small and distant, yet rich with meaning. Now, we've found pale blue dots of our own. Maybe not exactly Earth, but distant worlds that shimmer with the promise of familiarity. maybe the most powerful fictional world of all is Earth 2, the idea that somewhere, out there, is a world just like this one, with oceans and seasons, maybe trees, maybe sunsets, maybe something that once looked up at their sky and wondered if they were alone. You drift now out of the imagination cloud and back into the real stars, but a trace of story lingers behind. Every data point we find, every light curve, every atmospheric spectrum, it all began with someone dreaming about a planet that didn't exist, and daring to believe that it could. So tonight, before we return to hard science, give yourself permission to wonder, to imagine walking under two suns, to touch alien soil, to hear wind in a different language, to meet something that doesn't look like us, and realize it has a story too. Because long before we find our second Earth, we've already made thousands of them, right here in our minds. You're floating now in a quieter place. No flashing instruments, no dazzling stars, just space and math, and a deeply uncomfortable question. What are the actual odds of finding life out there? Not just planets, not just water, but life. Real, wriggling, evolving, opinion-having life. This isn't a fantasy anymore. You're not daydreaming about Star Trek diplomacy or interstellar fungus colonies. You're stepping into the strange, numbers-heavy world of the Drake equation. If you've never met the Drake equation before, prepare yourself. It's both delightfully straightforward and infuriatingly vague. Formulated by astronomer Frank Drake in 1961, it tries to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. It looks like this: n equals r times fp times ne times fl times fi times fc times l star. Don't panic, let's break it down. You're sleepy, not studying for a test. R is the rate of star formation in our galaxy. Fp is the fraction of those stars with planetary systems. Ne is the average number of potentially habitable planets per star with planets. Fl is the fraction of habitable planets where life actually develops. Phi is the fraction of those planets where intelligent life evolves. F is the fraction of intelligent civilizations that develop detectable communication. L is the length of time such civilizations release signals into space. Multiply them all together and you get N, the number of civilizations we might be able to chat with, or at least eavesdrop on. Sounds easy, until you start plugging in numbers. The first few terms? We've got a decent handle on those now. Star formation rate, about 1 to 3 new stars per year. Fraction of stars with planets, over 90% based on Kepler and TESS data. Average number of Earth-like planets per star, maybe around 0.2 to 0.5. That alone gives you tens of billions of potentially habitable planets, but then it gets murky. Very murky. The fraction where life arises is a complete mystery. We have exactly one data point, Earth. And here's the kicker. We still don't really know how life started here. It could be a fluke, or it could be as inevitable as clouds forming in a wet sky. Historians and biologists and chemists still argue whether life emerged from a lucky set of chemical reactions, or whether it's a natural chemical reaction that always happens given the right soup of molecules and enough time. If the second one's true, then life might be everywhere. Not just here, not just in our solar system, but everywhere. Life might be what planets do. Now you move to Phi, how often intelligence evolves. Again, only one data point. Earth's been around for 4.5 billion years. Complex thinking life. Maybe the last few million. Modern technology. A sliver of time. That doesn't exactly inspire confidence. Consider this. For most of Earth's history, life didn't get past algae and bacteria. Intelligence might be rare, not because it's impossible, but because it doesn't offer enough of a survival advantage to dominate. There's a theory that evolution doesn't favour intelligence unless the conditions are just right, and maybe we're just a weird exception, clever apes with thumbs and Wi-Fi. FC, the ability to communicate across space, adds another layer. Even if a civilization becomes intelligent, will it build radios? Will it send signals? Or will it develop some other form of communication? Quantum, biological, incomprehensible to us? Maybe they whisper with magnetic fields. Maybe they communicate by light patterns in coral. Or maybe they're just quiet on purpose. And then there's L, the big one. How long do civilizations survive after developing the ability to communicate? 100 years? 1,000? 10 million? If they wipe themselves out quickly, that dramatically lowers the chances we'll ever overlap. You imagine two flashlights flicking on and off in the night. Unless they shine at the same time, they never see each other. Some scientists argue that N could be huge, thousands of civilizations scattered and hiding. Others say N could be one, US, alone. Not because no one else tried, but because no one else made it past the test of fire and fear and fossil fuels. A quirky little tidbit. In 2016, two MIT researchers proposed the idea of superhabitable planets, worlds better than Earth for supporting life, slightly larger, more geologically active, orbiting long-lived stars. If life is common, these places might be even more alive than Earth. We might not be the gold standard, we might just be the first test draft. There's another, even stranger possibility. What if life isn't rare, but life as we recognize it is? You consider shadow biospheres, the idea that alien life could already exist on Earth, using biochemistry so different from ours that we've simply never recognized it. That life could exist based on silicon instead of carbon, or thrive in sulfuric acid, or need radiation instead of fearing it. Life might be adaptable far beyond our expectations, but we keep looking for it in the places that feel familiar. That's the core of the problem. Our only model of life is us. Our only example of habitability is Earth. We might be walking through a galactic rainforest thinking it's a desert, just because the life there doesn't look like squirrels and seaweed. Still, the Drake equation gives us something precious, a framework for thinking about the question. It lets us talk about life in terms of probabilities, not just poetry. It gives scientists a way to structure the most unanswerable of questions. Are we alone? You hover above the numbers now, watching them flicker. You see simulations running, probabilities changing with each new discovery. Every planet we find tweaks the equation. Every molecule we detect narrows the margins. With every new atmosphere, with every new detection, we're painting in the variables, slowly, precisely, hopefully. The Drake equation won't give you a definite answer, but it gives you a direction to look in, and maybe just enough reason to believe that the universe wants to be inhabited. So you sit in this inky quiet, letting the possibilities swirl, tens of billions of planets, unknown odds of life, and us peering out of our one tiny dot, asking the question over and over. Maybe life is inevitable, maybe it's rare, maybe it's looking for us too. You glide now beyond probability and peer into something much weirder. A universe where life doesn't just emerge independently, it travels. Where life isn't limited to the place it began, but gets tossed, flung, smeared across the stars like cosmic pollen. You've entered the speculative and deliciously fringe realm of panspermia, the idea that life might spread through space. It sounds like science fiction, or maybe a bad yogurt commercial. But panspermia is a real hypothesis, debated in the halls of astrobiology and planetary science. It asks, what if life didn't start on Earth? What if it arrived here, uninvited but determined, riding shotgun on a meteor or hiding in the cracks of a comet? Start with the basics. We know that rocks from Mars have landed on Earth. That's not a theory, it's a fact. Dozens of Martian meteorites have been found here, blasted off the surface of Mars by asteroid impacts, then drifting through space until gravity pulled them down through our atmosphere. Some landed gently enough to preserve complex internal chemistry. Now imagine that one of those rocks wasn't just rock. Imagine it carried something. Alive. Microbes are tough. We're talking about extremophils here. Tiny, ancient, ridiculously stubborn life forms. On Earth, they thrive in boiling acid pools beneath Antarctic ice, inside nuclear reactors, and under crushing ocean pressures. Some can survive space. In fact, in experiments on the International Space Station, tardigrades, your favourite microscopic space bears, survived exposure to the vacuum and radiation of space, then rehydrated like cosmic soup packets and got right back to wiggling. There are even bacteria on Earth that go dormant, forming spores that can remain viable for millions of years. They shut down like laptops in hibernation mode, waiting for the right conditions. Add water, add warmth, life resumes, which means, under the right circumstances, a microscopic life form could survive a trip between planets. Now imagine the implications. If Earth was seeded with microbial life from Mars, or somewhere even farther away, then we're not a unique beginning. We're a branch, a node in a web of interplanetary biology. We might owe our entire existence to an ancient spore hitching a ride across space. Historians still argue whether panspermia should be considered a scientific hypothesis or just a distraction from figuring out abiogenesis, the origin of life on Earth. After all, saying life came from elsewhere doesn't explain how it started. It just moves the goalpost. You still need that first spark, that first self-replicating molecule. But it's a valid idea, especially when you look at just how early life seems to have appeared on Earth. Our planet cooled enough for liquid water about 4.3 billion years ago, and by 3.8 billion years ago, maybe sooner, there were signs of microbial life. That's fast. Suspiciously fast, in fact. So fast that some researchers wonder if life didn't develop here at all, but showed up already prepared. You lean now into the deeper layers of this idea. There's lithopanspermia, the notion that life travels inside rocks. Asteroid impacts eject debris from a life-bearing planet. Some of that debris escapes into space. It drifts. Eventually it gets pulled in by the gravity of another planet. If the microbes survive the vacuum and the fiery plunge-through atmosphere, well, hello new biosphere. Then there's ballistic panspermia, the more aggressive version. Life gets launched, on purpose or by violent force. Giant impacts maybe. Or directed panspermia? Yes, that's when a civilization sends life elsewhere on purpose. Picture alien scientists filling probes with bacteria and launching them into promising systems, like interstellar sourdough starters. Sounds ridiculous? Nobel Prize winner Francis Crick, co-discoverer of DNA, once floated that exact idea. You know, just casually. Here's a quirky, very real tidbit. Earth might be sending life right now. Every rocket we launch to Mars is scrubbed and sterilized, but there's always a risk that a few hardy microbes hitched a ride. If we ever find life on Mars, scientists will have to prove it's not our life. Contamination from Earth pretending to be something new. But what if it goes further? Some theorists have proposed that interstellar comets, like Oumuamua, that weird cigar-shaped visitor we spotted zipping through our solar system in 2017, could carry organic material from other star systems, maybe even life. Imagine a comet from another galaxy, containing the microbial fingerprints of an alien ecosystem, silently cruising through our neighborhood, unnoticed for eons. Some scientists have even wondered if virus-like particles could survive deep space and be distributed through solar winds or radiation pressure. Yes, galactic viruses, the ultimate long-distance delivery system. And of course, now you're wondering if the flu is ever really local. A note of caution. Panspermia doesn't require intelligent life to be true. It's about biology being mobile. Life is something that doesn't just happen and stay put, but is something that moves, that spreads, that colonizes. Not out of ambition, but because chemistry is stubborn, and that changes how we think about the galaxy. Maybe we shouldn't expect to find a genesis of life on every habitable planet. Maybe many of them share a common biological ancestry, seeded from the same ancient source. Maybe we're cousins, not strangers. Or maybe panspermia explains why life appears to be so rare. Maybe it's a long game, a slow trickle, a single spark spreading across billions of years, lighting one planet, then another. Maybe we're not early, maybe we're just next. Of course, we have no proof, not yet. But future missions might start looking. Mars, Europa, Enceladus. If we find life on those worlds, and if that life uses DNA or has biochemistry suspiciously similar to ours, well, then the conversation shifts. Because either life arose independently multiple times using the same building blocks, or it's spread. You float now through that idea. Life as a traveller. Life as something not bound to one world. Something slow, patient, stubborn, and ancient, carried on rocks, comets, spores, or ships. And maybe one day us. Because once we start moving outward, really moving, really settling, maybe we become the new agents of panspermia. Not sending bacteria by accident, but carrying Earth's biosphere with us, planting it wherever we go. Life might not just spread across space. It might be destined to. You drift now toward a dry, cratered world. Not barren, not lifeless, just unfinished. There's light here, and rock, and gravity. But no breathable air, no oceans, no birdsong. Just a sullen silence that says, not yet. And that's where your mind turns to terraforming. The quiet, audacious idea that we might reshape a planet to make it home. Not find a second Earth, build one. Terraforming as a concept is one part science, one part madness, and at least 3 parts long-term optimism. It's the process of transforming a planet's environment, temperature, atmosphere, surface chemistry, until it becomes Earth-like, or at least survivable. The word itself was coined in the 1940s, but the dream, much older. Terraforming is just gardening on a galactic scale. Start with the easiest candidate, Mars, our rusty neighbour. It's cold, dry, and has an atmosphere about 1% the pressure of Earth's, but it has water in the form of ice, a day length close to ours, and a history that hints at rivers and lakes. Mars is like an abandoned house. You could move in, but the heating's busted and there's no roof. So how would you terraform Mars? Well, you could start by warming it up. One idea? Release super greenhouse gases, think perfluorocarbons, into the Martian atmosphere. These would trap heat far more efficiently than CO2, gradually raising the temperature. That could melt the ice caps, releasing CO2 already trapped there, which would thicken the atmosphere and warm the planet even more. A feedback loop. You'd still need a thick coat, but you might not die the second you step outside. Alternatively, we could build massive orbital mirrors, floating in space, focusing sunlight onto key regions of the Martian surface. Or crash ammonia-rich asteroids into Mars. Ammonia's a greenhouse gas too. Violent, yes, but effective. Terraforming, it turns out, isn't always gentle. Eventually you might have enough atmospheric pressure for liquid water to pool again. Maybe not oceans, but lakes, streams, puddles you could skip rocks across. And if the temperature rose enough and the air thickened and you seeded the ground with hearty Earth microbes, well, now you're cooking. Historians still argue whether Mars should be terraformed. Some say it's humanity's destiny to green the red planet. Others argue that doing so would destroy valuable clues about Mars' ancient climate, and maybe even native life. Terraforming in that view is not innovation, it's colonization. But Mars isn't the only candidate. Think about Venus, the opposite problem. It's too hot. Way too hot. The surface is over 450 degrees Celsius, hot enough to melt lead. The atmosphere is thick with carbon dioxide and sulfuric acid. Lovely place, great for saunas, terrible for picnics. To terraform Venus, you'd need to cool it down. Some ideas include installing orbital shades, massive reflectors that block or divert sunlight. Others suggest seeding the upper atmosphere with bacteria that could convert CO2 into oxygen. Wildest plan yet? Strip the atmosphere away entirely using massive magnetic fields or space-based scoopers. The scale is insane. The cost? You don't want to know. But if you could pull it off, Venus would be close to Earth's size and gravity. That's a prize worth fighting for. You don't have to stop with rocky planets either. Some theorists have looked at the moons of Jupiter and Saturn, like Europa, Ganymede and Titan, as potential targets. These icy bodies may hide subsurface oceans warmed by tidal forces. If you could warm the outer crust and thicken the atmosphere, you might not need full terraforming, just habitats on the surface. A kind of halfway home. Terraforming light. Here's a quirky fringe idea. Para-terraforming. Instead of changing the whole planet, you build a massive dome or shell over a part of it and create Earth-like conditions inside. It's less like fixing the weather and more like ignoring it. A city-sized snow globe with oxygen, pressure and little trees. Practical? Sort of. It reduces risk. Reversible. No waiting centuries. Just slap a bubble on it and move in. Of course, there's the timeline problem. Terraforming isn't quick. Some estimates say it could take hundreds to thousands of years to fully terraform Mars. Others say it might never be feasible at all with our current tech. Not to mention the ethics. Do we have the right to reshape entire worlds? Is that ambition or arrogance? And what if we get it wrong? Terraforming could create runaway effects. You might overshoot the greenhouse effect and boil your new home. You might unearth ancient toxins, or trigger dust storms that blot out the sun for decades. Planetary engineering doesn't come with an undo button. You float now through possible futures. One where humans live in giant climate-controlled domes on a half-warmed Mars. Another where floating cities hover in the Venusian clouds. Another still where we abandon physical terraforming altogether and choose to bioengineer ourselves to survive alien environments. Thicker skin, radiation tolerance, modified lungs, terraform the human, not the planet. Here's a wild but grounded idea. Someday, instead of sending people to terraform, we send swarms of machines, robots, nanobots, atmospheric processors. They crawl across the surface, building habitats, thickening air, warming soil, preparing for a future colony. The planet becomes a construction zone for a future no one living now will see. But maybe that's okay. Terraforming isn't about next year. It's about legacy. It's about planting seeds for a civilization that doesn't yet exist. Not just expanding, evolving, growing, becoming more than a single species, single planet culture. Because one planet, no matter how beautiful, is fragile, and Earth isn't a backup drive. You hover now above a cooling Martian lake imagined for now. You watch vapor rise into a deepening sky. You picture weeds, birds, trees. It's not real yet, but it could be. And it starts with us asking, what if we didn't just visit other worlds? What if we made them ours? Not through conquest, but through care, through time, through dreaming something big and then getting to work. You glide now toward a sobering horizon, far from the hopeful blue of imagined Earth twins or the green promise of terraformed valleys. Out here, between the stars, space reveals its harshest truth: distance. The sheer, cruel, laugh-out-loud scale of it. You've spent this journey exploring thousands of planets, peering into alien skies, and sketching the outlines of future homes. But now, you have to face the question that hums underneath all of it. How would we actually get there? And the answer, in almost every direction you turn, is the same. We can't. At least not yet. Let's break it down. The nearest known potentially habitable planet, Proxima Centauri b, is 4.2 light-years away. That's 40 trillion kilometers. You could drive there at highway speed in about 50 million years. Bring snacks. Even our fastest spacecraft like Voyager 1 would take over 70,000 years to reach that distance, and it's not even heading in the right direction. Light makes the trip in just over 4 years. Humans? Not so much. We don't have a ship, a fuel source, or a shielding system capable of making that journey even remotely realistic. The problem is energy. The faster you go, the more energy you need. But you can't just bolt a massive rocket to the back of a spaceship and hit full send. In space, fuel becomes mass, and more mass needs more fuel, and that fuel has mass too. It's a vicious circle that even clever math can't completely escape. Let's say you wanted to go just 10% the speed of light, enough to reach Proxima b in around 40 years. That's 30,000 kilometers per second. At that speed, a collision with even a tiny particle of dust could cripple your ship. Space isn't empty, it's full of invisible shrapnel. To survive, you'd need some kind of deflector shield or ablative armor, which adds more mass, which needs more fuel. And here we go again. You've just entered the cursed territory of interstellar engineering. So what are the options? Well, first, there's chemical rockets, the kind we use now. Good for Earth orbit, good for moonshots. Absolutely useless for interstellar travel. They just can't carry enough fuel to keep going that long. It's like trying to drive across the country with one gas station and no rest stops. Then there's ion propulsion, like what NASA's Dawn spacecraft used. Very efficient, very slow. It accelerates gently over months or years, reaching decent speeds eventually, but nowhere near what you'd need for interstellar distances. Great for in-system travel, not great for jumping to the stars. Next, the science gets weirder and better. Fusion propulsion is one of the most promising ideas. It's based on the same principle that powers the sun, fusing light atomic nuclei to release energy. Theoretically, a fusion-powered spacecraft could reach 10% to 20% the speed of light, making nearby stars reachable in a human lifetime. But fusion propulsion is still in the lab, and barely there. We haven't even built a working fusion reactor that produces more energy than it consumes here on Earth. But we're trying. One of the earliest interstellar concepts was Project Daedalus, a 1970s British Interplanetary Society study. It proposed a fusion-powered spacecraft that could reach Barnard's star in about 50 years. Uncrewed, of course. No way to slow down. Just fly by, take pictures, and weep softly into your data stream. More recently, there's Breakthrough Starshot, a real current project funded by billionaires and advised by actual physicists. The plan? Build gram-sized spacecraft, tiny chips with cameras and communication gear, and launch them using ground-based lasers. The lasers would blast them up to 20% the speed of light, sending them flying toward Proxima b in just 20 years. Sounds amazing, right? But it also means your spaceship has no propulsion, no brakes, and is roughly the size of a tortilla chip. You get one blurry snapshot of an alien world before your craft zips past it forever. Still, it's better than nothing. It's the most practical interstellar mission we've ever seriously considered. Of course, there are the madder ideas. Antimatter engines could, in theory, deliver enormous energy per gram. Matter and antimatter annihilate each other completely, turning into pure energy. 1 gram of antimatter could power an entire city for a day, or hurl a spacecraft across space at astonishing speed. The catch: antimatter is outrageously expensive to make, and storing it safely is, well, good luck with that. Or what about warp drives? The idea that you could bend space itself, contracting it in front of you and expanding it behind, moving without technically travelling faster than light. The famous Alcubierre drive exists purely in math and requires negative energy, something we don't know how to create, let alone control. Historians still argue whether warp drives are possible or just theoretical teases, but scientists like Harold White at NASA have been trying to refine the idea, looking for a version that doesn't require absurd physics. So far, no warp. But hope remains irrationally persistent. Then there's generation ships, giant self-sustaining vessels where entire civilizations live and die en route to another star. Maybe the original crew never sees the destination. Their grandchildren are born in metal corridors, grow up under artificial skies and inherit the mission. It's a beautiful idea. Also a horrifying one. What happens when someone decides to turn the ship around halfway through? What happens if they forget why they left? Or, more optimistically, what if we never send humans at all? What if our first visitors to other worlds are robots, AI, or even digitized consciousness? Upload a mind, launch it as data, let it wake up in a synthetic body light years away. No air needed, no water, just code, memory and curiosity. But the sobering truth remains. For now, and possibly for a very long time, the stars are unreachable. You stand now on the edge of that realization. Thousands of habitable planets out there, hundreds of promising ones, and you, trapped on a pale blue dot with no interstellar Uber. But strangely, that makes the search feel even more precious. Every spectrum, every light curve, every faint dimming of starlight, those are our only contact points with these distant worlds. We can't go there yet, but we can know them, study them, imagine them, prepare for them. Because one day, maybe in 100 years, maybe 1,000, someone will solve the propulsion puzzle. Someone will break the curse of distance. Someone will leave, carrying not just machines or microbes, but stories. And maybe, just maybe, they'll land. Until then, we watch, we wait, we dream. Because even if we can't go to them, those planets are still out there, and they are not waiting. They are becoming. You hover now in the quiet between stars, not to travel but to talk. If we can't go to the planets yet, maybe we can call them, or at least shout into the void and hope someone somewhere hears us. This is the art and heartbreak of interstellar communication, the attempt to send messages into space, like bottles tossed into an eternal ocean. And the truth? We've been leaking signals for decades. Your favourite sitcoms, FM radio, World Cup broadcasts, all of it has been radiating into space since the 20th century. Earth is wrapped in an expanding sphere of electromagnetic noise, roughly 100 light-years wide. Any civilization within that sphere, with a big enough dish and a lot of patience, could be listening to our culture in reverse order. Seinfeld, Super Bowl III, a 1984 weather report. It's not exactly Shakespeare, but it's honest. This unintentional leakage is called radio leakage, and it's faint. The signals weaken dramatically with distance. After just a few light years, most of it is buried in the static of the cosmos. So while we've been noisy, we haven't exactly been noticeable. If you're listening from Proxima Centauri, you'd need a truly massive antenna to detect reruns of Gilligan's Island. But then there's the deliberate stuff, the messages in bottles we've actually tried to send. The most famous of these is the Arecibo message, transmitted in 1974 from the Arecibo radio telescope in Puerto Rico. It was a tightly packed 3-minute burst aimed at the M13 star cluster, about 25,000 light-years away. The message included binary encoded information, numbers, chemical elements, a human figure, DNA structure, and a graphic of the solar system. Smart, concise. Also, unlikely to ever be answered, because M13 will have moved by the time the signal gets there. Still, the gesture was poetic. We said, "Hello," and we meant it. Then there are the Voyager golden records. Launched in 1977 aboard Voyager 1 and 2, these are literal records, gold-plated LPs containing images, music, greetings in 55 languages, and sounds from Earth, laughter, thunder, wails. One of them is now over 15 billion miles from Earth, racing through interstellar space. It might last for billions of years, a mixtape from a tiny blue world drifting through the dark. Here's a quirky, deeply human tidbit. The golden records include a diagram of a naked man and woman. In 1977, NASA's team was so worried about nudity being controversial that they removed it from the Voyager plaque. But later, on the record, they quietly added a medical drawing of a male and female silhouette. So yes, if aliens ever find Voyager, their first impression of us might be awkward health class diagrams. You're welcome, galaxy. More recently, we've sent messages from powerful radio telescopes, Cosmic Call, 1999, Teenage Message, 2001, and the Across the Universe Transmission, 2008, which beamed a Beatles song to the star Polaris, because if anyone's going to break the silence, let it be John, Paul, George, and Ringo. But here's the debate that splits scientists like a space-themed soap opera. Should we be sending messages at all? Some argue yes. After all, we've already leaked so much that we might as well introduce ourselves properly. Others, like Stephen Hawking, warned that broadcasting our existence could be dangerous. What if someone hears us who isn't friendly? What if we're waving at sharks? It's the SETI versus METI debate. SETI, Search for Extraterrestrial Intelligence, wants to listen quietly. METI, Messaging to Extraterrestrial Intelligence, wants to speak loudly. Historians still argue which is more responsible, or more optimistic, or more absurd. But SETI has its own romantic agony. Since the 1960s, massive radio dishes like those at the Allen Telescope Array have been listening to the stars, sweeping through frequency bands where intelligent signals might hide. The search focuses on narrowband signals, those that appear in a very specific frequency range, unlikely to be caused by natural processes, and sometimes something weird shows up. The most famous case? The WOW signal, detected in 1977 by Ohio State University's Big Ear Radio Telescope. A strong narrowband radio signal, lasting 72 seconds, from the constellation Sagittarius. Never repeated, never explained. The astronomer who spotted it in the data scrawled WOW next to the signal, hence the name. To this day, no one knows what caused it. A glitch, a passing satellite, an alien hello, no one can say. But it remains the closest we've ever come to a candidate signal. Others have emerged since, short bursts, repeating fast radio waves, signals that blink and vanish. Most are traced back to pulsars or human interference, but a few still sit in the we don't know pile. Here's another twist. We now search in optical and infrared light too, not just radio. Lasers, for instance, might be the signaling method of choice for advanced civilizations. They're fast, focused, and can be used like interstellar Morse code. But again, we haven't seen any laser beacons from Alpha Centauri. Not yet. The trouble with all of this, sending or listening, is the time involved. Say we send a message to Proxima Centauri. It takes over 4 years to get there. If someone answers right away, it's still 8 years round trip. Now scale that up. A message to a planet 100 light years away, you'd need 200 years just to get a reply. Imagine writing hi and waiting 2 centuries for someone to write back sup, and yet, we still try, because we want to be found, or at least remembered. It's the most human thing we've ever done. Shout into the void and hope the void says hi. Some dream of the day we detect a signal we can't explain, a steady pulse, a deliberate pattern, a message in binary, or a song, or silence interrupted by meaning. Something that says, you're not alone. We see you. We are here. Others say we may never hear anything, that civilizations are rare, or too far, or simply not interested. Maybe they've moved beyond electromagnetic communication. Maybe we're still shouting in a language they've long forgotten. But for now, Earth keeps humming. Radios buzz, data flows, telescopes listen, and maybe somewhere something listens back. You float now in the stillness of deep space. Far ahead, light passes through the dark, coded, quiet, hopeful. A signal, maybe ours, maybe theirs. Either way, we've said hello. Now we wait. You coast now through the deepest silence of all. No radio waves, no cosmic songs, no signs of spacecraft. Just the eerie stillness of the galaxy, a place packed with stars, planets, habitable zones. And yet, no one answers. You've reached the crossroads of curiosity and cosmic anxiety, the Great Fermi Paradox. It's named after physicist Enrico Fermi, who, over lunch in 1950, famously asked a question so sharp and simple that it's haunted astronomy ever since. Where is everybody? The logic behind it is brutal in its clarity. There are billions of stars in our galaxy. A large fraction of them likely have planets. Many of those planets are Earth-like. Some percentage should have developed life. Some of that life should have become intelligent. Some of those intelligent beings should have built technology. Some of them should have spread out. And yet, here we are, alone, no visitors, no messages, no ruins, just a persistent galactic-level ghosting. Statistically, the silence doesn't make sense, and that's why the Fermi paradox is so unsettling. It's not about whether aliens exist, it's about why we haven't seen any trace of them if they do. So, what's going on? Well, there's a list. Dozens of potential answers, each more intriguing and occasionally terrifying than the last. Let's start soft. Maybe we just haven't looked long enough. Our technological civilization is barely a century old. We've had radio for a cosmic blink. Our telescopes are only now becoming powerful enough to read atmospheres of distant worlds. We've explored exactly 0 exoplanets up close. The galaxy is huge. The silence might just be a matter of timing. Or maybe we're not listening the right way. We've focused on radio waves, lasers, and atmospheric signatures. But what if aliens use entirely different technologies? Quantum entanglement, neutrino pulses, gravitational wave modulations, signals that pass through us unnoticed, like shouting at a dog using colours. Here's a quirky thought. Maybe the galaxy is full of signals, but we don't recognise them because they're embedded in nature. Some researchers have suggested that pulsars, those spinning neutron stars that emit rhythmic signals, might have been mistaken by early astronomers as alien beacons, and maybe they are. Or maybe some other natural phenomena we've labelled are actually techno-signatures in disguise. Now let's go darker. Maybe there were civilizations, millions of them, but they're gone, destroyed by their own technology, climate collapse, war, or something we haven't imagined yet. This leads us to the idea of the Great Filter, the concept that there's a stage in the evolution of life that's incredibly hard to survive. If that filter is behind us, say, the origin of life, or the leap to multicellular organisms, then we're the lucky ones, survivors, the first to pass through. But if the filter is ahead of us, nuclear war, rogue AI, planetary destruction, then we may be doomed just like the rest. The silence becomes a warning. Some scientists and philosophers argue that the absence of detectable alien civilizations is bad news. It means intelligent life either wipes itself out, or something else does. A cosmic predator, a sterilizing wave, a quiet force that deletes civilizations before they go interstellar. Others propose more hopeful explanations. Maybe aliens are out there, but they're observing us quietly, like wildlife researchers hiding in the bushes. This is the zoo hypothesis, the idea that Earth is under quarantine, too young, too dangerous, too chaotic. We're not ready to join the galactic conversation. The aliens are watching, taking notes, rolling their eyes. Or maybe civilizations evolve into such radically different forms that we can't recognize them. They upload into virtual realities, shrink themselves into nanostructures, live in black holes for the gravitational aesthetic. They're still here, but they're no longer playing the same game. There's also the forest hypothesis, and it's a little more chilling. It suggests that the galaxy is like a dark forest. Every civilization is a hunter. You never announce your presence, because if you do, someone else might find you and shoot first. Silence, then, is not mystery. It's survival strategy. You float now in this imagined forest. Trees are stars. Beneath each canopy a possible intelligence, quiet, listening, never daring to light a fire. Earth, naive and bold, has already shouted into the woods, "Oops," and yet we continue. Despite the silence, despite the risk, we listen, we broadcast, we search. Here's another idea. Maybe we are the first. Not just in our corner of the galaxy, but anywhere. Maybe intelligent life takes a long, long time to appear. Maybe we're witnessing the universe still in its awkward teenage years, and civilizations are just now beginning to spark. We might be the early risers. And if that's true, then it's on us to reach out, to explore, to keep the light going. Historians still argue whether the Fermi paradox is even a paradox at all. Some say the lack of contact is exactly what you'd expect in a young, sparse, enormous galaxy. Others think the silence is deafening and demands explanation. But here's the twist that always lingers in the background. Absence of evidence is not evidence of absence. We've barely scratched the surface of what's out there. We're guessing at shadows, listening with ears not yet tuned. You now imagine a distant planet orbiting a quiet star, its skies filled with data. Maybe there was life. Maybe there is. Maybe a signal was sent centuries ago, still on its way. Maybe it'll reach us tomorrow, or in 100 years. Or maybe the answer is simpler. We're alone. For now. Not forever, not by design, just for now. Because the stars don't owe us answers. They owe us time. Time to keep listening, time to grow our reach, time to build better ears. So tonight, as you float in the stillness, know that the silence isn't final. It's a pause, a breath. And in that breath, there is still so much we can find. You're drifting now toward the question that's been quietly humming beneath all the science, all the speculation, all the staring into star-studded darkness. A question both massive and oddly personal. What are the odds of finding another us? Not just a planet with the right chemistry, not just microbial slimes or rogue bacteria hiding under ice, but a planet where something, someone, looks up at their sky and wonders, just like you do, if they're alone. It's the gold medal in the great cosmic hunt, a second Earth, with a second intelligence. But what would that actually mean? Let's start simple. If we define another us as a planet that supports intelligent, self-aware, technologically capable life, we're asking for a very specific cocktail of conditions. You need the right star, the right planet, the right distance, a stable orbit, plate tectonics, a magnetic field, liquid water, atmosphere, climate cycles. Enough time, billions of years, for life to not just appear, but evolve. Then you need filters, biological ones, evolutionary choke points. Life has to move from simple to complex, from single-celled to multicellular, from survival instincts to tool use, from fire to cities, from caves to satellites. And all of that has happened once that we know of. Here's the kicker. Earth may not even be Earth-like, not in the statistical sense. Some researchers think Earth might be an outlier, too tectonically active, too rich in radioactive elements, too stabilized by its moon, too lucky to have just the right kind of star in just the right part of the galaxy at just the right time. Historians and exoplanet scientists still argue whether Earth's characteristics are typical or rare. We used to assume Earth was the blueprint for life-bearing worlds, but now, maybe it's just one possibility out of millions, a winning lottery ticket in a cosmic raffle no one knows they're holding. But then, Earth exists, and we exist, and the universe is old. There are stars out there billions of years older than our sun, planets that have had longer to evolve life, civilizations, if they exist, that could be millions of years ahead of us. So if intelligence isn't rare, where are they? And we're back to the Fermi paradox, the great silence. Maybe the odds of intelligent life developing are high, but the odds of intelligent life surviving its adolescence, much lower. We look around and see a species, us, that has come dangerously close again and again to self-extinction. We build tools faster than we build wisdom. We invent weapons before we invent safety nets. And maybe we're the rule, not the exception. Maybe the galaxy has dozens of failed Earths, planets where life bloomed, thought, sang, and then vanished. One short scream of civilization, followed by silence. Or maybe the odds are higher than we think and the recognition is the hard part. Let's say we do find a planet. Right size, right temperature, biosignatures in the atmosphere. Maybe even technosignatures, radio waves, pollution, blinking lights on the night side. Would we know what we're seeing? Imagine trying to understand human civilization from hundreds of light years away, using only faint spectra and weak signals. Now flip that. Imagine alien life using communication methods we can't detect. No electricity, no metal. Maybe they think in chemistry. Maybe they evolved in a deep ocean with no air, no fire, no physics like ours. Could be they built cities of coral and passed knowledge by touch. Maybe they never developed electronics because they never needed to. Would we even recognize them as intelligent? Here's a quirky twist. Some researchers are now looking into non-technological intelligence. That is, life forms that are sentient but never become advanced. Think of whales, octopuses, elephants, creatures with memory, social structures, even language, but no cities, no spaceships. So if we find signs of life on a distant exoplanet, methane, oxygen, maybe even seasonal changes in the atmosphere, what are the odds we're looking at another us? The truth. Tiny, but not zero. And that not zero is why we keep searching. Because even one other civilization, just one, would mean the universe isn't silent or cold or indifferent. It would mean there are other minds out there, other stories, other dreams. And if we found them, what then? Would we reach out, send a message, wait for a reply? Would we try to understand them, or just study them, like bugs behind glass? Would we share ourselves, our art, our pain, our music? Would we tell them we have oceans and laughter and terrible movies and people who cry when they hear a certain chord in a certain song? Would we listen to their songs, or would it be more quiet than that? Just a distant dot in the sky with a strange little blip in the atmosphere, a trace of thought, a breath of culture, a faint, flickering yes. No conversation, no reply, just the knowledge. You float now above that possibility, the mathematical whisper that somewhere across the galaxy there's another us. Maybe it's rare, maybe it's inevitable, maybe it's already happened 1,000 times, or maybe it's waiting, a second Earth, a second chance, a second mirror in the dark, and you're here, alive in the one moment in history where we're finally able to look. Not blindly, not hopefully, but methodically, brilliantly, humanly. The odds might be small, but they're not zero, and that's enough to keep listening. That's enough to keep watching. That's enough to believe. And now, everything slows. You let go of the numbers, the theories, the ships and stars and questions too big to hold. You're drifting weightless again, wrapped in the soft hush of deep space, where silence isn't absence, it's peace. The hunt for a second Earth stretches far beyond your reach tonight, far beyond the instruments, the debates, the late-night data streams. It's a journey of patience, of wonder, of looking up again and again, even when nothing blinks back. But you've travelled far. You've stood beneath alien suns, floated through clouds made of glass and carbon, glimpsed shadows of distant worlds not through science fiction, but through math and mirrors and light bent across time. You felt the ache of wanting to know, not just if we're alone, but what it would mean if we weren't. You let that weight fall away now. No need to answer anything, not tonight, not here. Let your thoughts settle like dust on a quiet planet. Let the vastness of it all become background hum, the kind that doesn't ask anything of you, the kind that holds you gently in its enormity. Somewhere out there another Earth might be turning, but for now this one is enough. This gravity, this air, this heartbeat. So breathe, sink into the dark, and let the stars watch over you.